some sample multiple choice questions here. First things first, yes, you'll see there is some math that you will have to do here, but they use very easy numbers, so it should be very obvious to you. I mean, we're talking little decimal math here that you should be able to do. And if you don't remember these kind of things, it's a good time to start brushing up on it, since obviously you won't be able to use your calculator on this particular test for the multiple choice section. So up here they give you a little diagram, the N02 and the N2O4 reaction. As you can see, lots of these equilibrium reactions get repeated over and over again, but it gives the diagram which tells us the what? Well, it tells us the number of particles in the container. It also told us what about the container? That is 1 liter. So yes, now we can figure out the concentration or a generalized idea of the concentration. So we count our little NO2 dots. We have 6, and if we count our N2O4 dots, we have 3, right? So that's basically, 3/1, 3m, and our, 6/1, 6m, which is fine. Now, what does it want us to do here?
Find K.
Basically, we have to find K because we have to decide if K is, one of these values over here. So which of the following must be true about the value of the equilibrium constant? So if you're following the law of mass action, we have K equals the NO2. Well, that's the reactant, sorry. Let's put that on the bottom. NO2 squared, concentration of N2O4 on top. So basically what we have here is 3 divided by 6 squared. Do I even really have to calculate that? No, I don't, because that's going to give me a number that is less than 1. And it's obviously going to be then which answer? B. So that would be the correct answer there.
I have a question.
Yes.
If a multiple choice question ever gives you the option to pick the answer based on enough information, is that ever the right answer?
Not usually. Not usually. There occasionally, but not usually. All right, looking here at this one, we have, hydrogen iodide breaking apart into hydrogen and iodine gas. They gave us what here to look at?
All the initial concentrations.
They gave us initial concentration, so this is obviously a Q problem, but you could probably tell that based off of your answer choices here too, because it's comparing pretty much everything to K to Q there. So what do we need to do? We need to calculate Q. Let's go ahead and we're going to put the product value, first product value on top, second product value, and our reactant goes on the bottom, and that's going to be squared because balanced reaction, there's 2 moles of that. So basically, what are we getting here? 0.05 over 4. What is that going to give you? Well, if that math is like, wow, I can't think like that, well then what is 5 divided by 4? 1.25, but this is 0.05, so all you have to do is move it over 2 spots to the left. This is how you do that mental math faster, right? So Q is 0.0125. What's K again? What did they tell us K was?
0.020.
Up here. So obviously K is greater than Q here, because this is the 0.25. So out of our choices here, we know Q is less than K. So we could cross off that one, that one, that one. If K is greater than Q, which way is it going to proceed?
Probably, so it's B.
therefore it has to be B. Correct. This is a very good Le Chatelier type problem that you'll see. Kind of meshes all the concepts together because it's giving you a reaction that's endothermic. It's giving you one that has all gaseous moles in it. So you're going to pretty much go step by step through it. Given the forward reaction is endothermic, so where am I going to put the heat? On the reactant side, yes. Heat or energy goes over here. Which of the following will decrease the equilibrium amount of H2O? So we need to have this guy decreasing. Now there's 2 moles of gas here to 3 moles of gas over here. You can set yourself up nicely to get ready to do all of the concepts together. Although before you even begin, you can eliminate which 2 offhand. Adding the HE gas, yes, that is, you know, inert gas. That one's not going to work because that doesn't change anything. What else? B, adding a catalyst, it speeds it up in both directions equally, so that also has no change or effect. So now, if we add an oxygen, we're adding over here, which way is that going to proceed? Towards the reactants, does that increase or decrease the water? Increase the water vapor. Okay, so that one doesn't work. Decreasing the volume of the container so the total pressure increases.
When pressure increases, it goes to the side with the least amount of moles, so that will work.
Yes, so this is also going to shift towards the reactants, creating more water vapor because going to the side with fewer moles. Very good. And so our last option here, which is definitely going to be the right one, but let's make sure it is, increasing the temperature. So basically you're adding in heat, adding that should proceed towards the product, therefore decreasing the reactant, which happens to be the water vapor. So this is a very good example of how they do the Le Chatelier multiple choice questions. Now for the very fun one. And they'll sometimes have a series of multiple choice questions off of the scenario like this one. I only put 2 in, but sometimes there's 3 or 4 off of the same, you know, setup here. We have, of course, our water vapor breaking apart into hydrogen and oxygen gases. And it tells us figure 1 is initially what's in the container and the initial pressure. Over here it's telling you at equilibrium what you have in the container, these 3 things, and its total pressure. So at equilibrium and what you have initially. So let's look at the first multiple choice question. Which of the following statements is correct about Kp? The equilibrium constant for the reaction is correct. So we need to figure out what?
The
Kp for equilibrium. They didn't give us a lot of information here. So what should we set up? What should we set up? The rice table. Yes, let's organize our information. Yes, and we are going to be working with those partial pressures. That's true. So rice. Like so. Initially, what do we have?
2 ATM of H2O.
ATM here, right? So these guys have to be over here on the right are at 0 pressure. Good. Now we just put in our change. So we know it's going to proceed towards the product. So minus 2x plus 2x plus x. Now down here, that ends up being 2 minus 2x plus 2x plus x at equilibrium. What is the only other piece of information they're telling us here?
P total.
The P total at equilibrium. And what do you know about partial pressures of gases in a mixture like that?
You can just add, yeah.
Because which law can we use here?
The
Dalton's law of partial pressures. So these should all add up to
2 plus X.
Yes, and so when you're doing this, obviously, the plus 2x and the minus 2x now cancel out. So really, what we have here is 2 plus x equals 2.5. So what is x?
0.5.
X is going to be 0.5 ATM. Now that we know the change, we can figure out the equilibrium concentrations. So this one, 2 minus 2 times 0.5 gives us 1. This one is 2 times 0.5, which is also 1, and this one's going to be 0.5. So now we can figure out our equilibrium concentrations. Very easy numbers too. So now you can calculate Kp. So our 0.5 times our 1 squared over 1 squared, right? So what is Kp going to be? Kp is going to be 0.5. So obviously it is less than 1. So yeah, that one's a lot of work, and you might not have thought, oh, Dalton's law of partial pressure, but you can definitely use that there. They love to shove in those gas laws when they can, making the concepts blend together. Yes. Question.
Would further tests be like one of the problems that, in your opinion, you would just get like saved for later? Like this one takes like a lot more time than like one just.
Yes, that would be good time management. And also, like I said, usually a scenario like this is going to have like 3 or 4 multiple choices attached to it. But as you can see in the next one here, the next example problem 5, this one really you don't need to know the answer to the other one in order to figure out. So you could skip the longer math problem 1 and come back to it at the end. It would definitely improve your chances of getting more of your other questions answered correctly. But, you should, try to get to it as well eventually, So here, still applying the same scenario, but it is a totally conceptual question. There isn't any math involved here. You just have to think about it. Which of the following is most likely the cause for the increase in pressure observed in the container as the reaction reaches equilibrium? Well, we have 2 ATM to start with. We have 2.5 at equilibrium. What is pressure caused by? Molecules hitting the walls of the container. And you didn't, change the volume. You didn't change the temperature. The only thing is you put the water vapor in there and let it do its thing. So what happened? The water vapor ended up, well, it started breaking down into H2 and O2. So in that process, we ended up with 2.5 ATM, and we have all 3 molecules present. So that means, obviously, that there are now more molecules inside that container. And if there's more molecules, they're going to hit the walls of the container. Yes, the first 2 are pretty obvious, no choice. They're definitely incorrect. The last one, D, is the only other one that seems possibly correct, but what's wrong with D?
It doesn't matter how hard they're hitting the wall.
It doesn't say anything about changing temperature. And temperature, remember, is the measure of the average kinetic energy of the molecules, so the speed doesn't change. So that's the one where that's the not obvious wrong answer that you have to really think about. So yeah, an increase in the number of molecules because you created some H2 and O2. And so you have a little bit more extra molecules in there than you did beforehand. That's going to, of course, cause more collisions, and C would be the correct answer. Now, hopefully this is an obvious one to you, but I'm putting it up here just in case. For specific reaction, which of the following statements can be made about K, the equilibrium constant? Yes, it's the only thing that's going to change C is temperature. It doesn't always remain the same at different conditions because temperature does change it. It increases if the concentration of one of the products is increased. We know that's not true. The only thing that can change K is course, is temperature. Increases concentration where the reactants is increased, also not gonna affect K. May be changed by the addition of a catalyst.